All right. So let's start. Welcome to the third lecture. So I thought to start this third lecture would be a good idea to give a summary of all that we did in the first two lectures. So we looked. Sorry, we looked at the modeling of the gravitational wave response in LISA, and then we looked at the modeling of the noise. We modeled the noise, and we derived different TDI variables in different generations, and we looked at the noise response in all of these variables. And at the end, we showed that in order to reduce the laser phase noise to well below the other noise sources, you really needed to go to the second generation variables and implement exact time delays. So what that means is that if you have real data from LISA and you want to make a measurement from this real data, you really need to go to the second generation and implement those time delays. Yeah.
So at the very end, would the LISA stream supply one data stream or a combination of data streams?
So there will be different levels of data depending on if you want if you want to really look at the output from every phase meter separately and reconstruct everything yourself, that would be possible, but they will provide different levels of reconstructions, like the X, Y, and Zs will be directly available, for example. Right. So if we implement this second generation TDI variables, then we can neglect the laser phase noise. Right. But if we assume that we have some data, say in a second generation TDI variable that's devoid of any laser phase noise because we've reduced it, then we saw, we saw also yesterday that we saw also yesterday that in the approximation that the triangle is equilateral, then the different generation TDI variables are proportional to each other. So for example, here x tilde is proportional to mx tilde. And same thing for the second generation variables. X tilde 1 is proportional to x tilde. So what that means is that if you have data with no laser phase noise in it, then you can do your data analysis with any generation variable that you like, as long as you stay consistent with the noise levels that you assume in your variables. Right. So the short summary, if you want to do simulation and simulate data and try to recover it, you can use the simplest TDI variables, and the result that you will get at least to leading order in the spacecraft orbital eccentricity and velocities will be the same as if you used the most complicated TDI variable. All right. So, so at the end yesterday, we looked at the structure of the gravitational waveforms. In the Inspiral, you have a sum of harmonics of the orbital phase. You're affected by Redshift. That's very general, and that prevents you from measuring the intrinsic masses directly. What you measure are redshifted masses like this. We described the effect of spin precession, how it affects the waveform, eccentricity, and we looked at the gravitational waveform in the Ringdown case after the merger. Right, so as an example, so here is something that will be useful to try to look for precursors for supermassive black hole mergers, is to look at how far ahead of the merger you can detect your signal. And this is what is shown in this plot as a function of the mass. This shows how far away you can detect a signal of a given mass 1 minute before merger, 1 hour, 1 day, 1 week, 1 month. And what you see is that really most of your signal here above, say, 10 to the 4 solar masses, most of your signal comes from the merger. And there was a question this morning. So at Redshift 20, the masses that you can observe is between, say, 10 to the 3 and 10 to the 7, if you're optimistic. Right. So, but even 1 day before merger, which would be at least useful, you still have accumulated only 1/10 of your total SNR.
This is the 1 minute exercise from the merger or the start?
That's the delay from the merger. Yeah. Yeah, so yeah, 1 minute before merger, you can see 10 to the 5 solar mass binary at Redshift 15.
Interesting to compute, for example, angular resolution, like one.
Yes. Yeah, that's also so. I haven't done that, but I believe that I have some collaborators who are working exactly on that, because that's.
All is published? All is published?
This is not published. This is a plot that I made when we wrote the proposal for Lisa, but we just to see. So no, I made this when we wrote the Lisa proposal, but it's not in there. It was just to get an idea of how far ahead you can get your trigger.
And the mass is redshifted mass or source?
That's intrinsic mass, I believe. Yeah. Yeah.
Things are equal. The two black holes are equal mass.
I think the mass ratio is 1 to 3. Yeah.
The more massive the binary is, the more massive the binary is.
Yes.
The higher the SNR, right?
No, not really. It depends. So here you see that the highest SNR that you get is 10 to the 4 solar mass black hole at redshift 1. So yes. So if you see a 10 to the 4 solar mass black hole at redshift 100, that means that the redshifted mass that you observe is 10 to the 6 solar masses. So this is the furthest away that you can see your signals. So that means that 10 to the 6 solar masses, say between 10 to the 6 and 10 to the 7, that's the loudest signals that you observe. Yes?
So, does this mean that you won't have a warning of the signal, let's say 1 minute before?
Yeah.
See it like you do with LIGO.
Yeah. Yeah, that's right. Except, well, I mean, so 1 day before, you can still reach redshifts above 5 between 10 to the 3 and 10 to the 7. Right? So.
But how, so you're chosen as SNR of 10, which is like what
Yes.
for LIGO. But given the, do we know, given the noises, phonics, and so on, what could be the false alarm? So there is.
Yes. So I think the threshold depends mostly on the complexity of the waveform more than anything else. So here it might be a little bit different because those will probably include eccentricity. So the signal-to-noise ratio threshold will probably be slightly higher than for LIGO, but SNR of 10, I think that's reasonable. For EMRIs, you get a threshold of 20, and that's and in terms of complexity, that's a completely different world. So.
And this uses IMR, so optimal SNR using Inspiral merger Ringdown.
Yeah.
So what rejection factors that could complicate eccentricity is one.
Yes. So for these systems, I think that's the main source of complexity, extra source of complexity compared to LIGO. For other kinds of signals like EMRIs, you have for extreme mass ratio in spirals. So when you have 10 solar mass black hole falling into a 10 to the 6, there you have very, very rich dynamics with resonances between different frequencies, and it's much more complicated to model, and that's why we will get more likely to get a higher false alarm rate. Right? Okay. So now let me present a study that we did to try to assess the capabilities of LISA in terms of parameter estimation for supermassive black hole binaries. So we used, we studied different black hole seeds model, like Priya was talking about this morning. We had a light seeds model with seeds coming from POP3 star remnants that were created between redshifts 15 and 20 at around 200 solar masses. And we had a heavy seed scenario with black holes present at redshift 15 to 20 with a mass already of 10 to the 5. One thing that came up is that delays between the galaxy mergers and the supermassive black hole mergers might be very, very important for the merger rates. Because if you so you simulate your galaxies, and you have two galaxies merging. That will still take hundreds of mega years to giga years in order for the black holes to sink down to the center and merge. So you will have some delays, and depending on the efficiency of the processes that drive the supermassive black holes to the center, you can have significant time delays or not. What came out was that in the light seed scenario, the delays were less important because the time scales for a lower mass black holes are much smaller. But for heavy seeds, it had a really large impact. Yeah.
What do you assume for binary thing? So, what? So, do you
For?
What fraction of these
Of these
black holes are in binary?
So these black holes are created at the center of galaxies in the early universe, and they merge when the galaxies, the host galaxies merge. Right.
This is like rates are obtained from like some simulation.
Yes. Yes. These were obtained from galaxy evolution simulations.
And the mass ratio is sort of let's assume like the black hole mass ratio.
So that depends. That depends on which galaxies merge, because each galaxy has a different mass black hole at the center, and when they merge, that will fix your yeah.
Somebody uses this model, is it like, can you use like a nearly equal mass assumptions to add?
I mean, you would probably really want to use the mass ratio in that case, because that has an effect. And I mean the mass ratios. So I don't show it here, but it varied from equal mass to 1 to 50 or something like that. You can generate high mass ratios with that. If you have a small galaxy that merges with a large galaxy, then you're
Generally, those type mergers are more common.
Yeah.
Right, in galaxies.
Yeah.
So you can have many more.
Yes.
Disparate mass black holes.
Yes.
Compared to equal mass black holes.
Yes. All right. So what we see here is that so first the light seed scenario predicts the largest merger rate. That's it's probably to be expected. We need to grow those black holes much more during the up to the present. And it peaks around redshift 8 to 10. That's where most of your mergers happen. In the heavy mass case, if you ignore the delays, your peak of the merger rate is around redshift 5, but stays roughly constant between redshift, say, 3 and 12. So,
are these the same models as we are talking about?
There's similar models. They're very similar models. They probably have some different subtle assumptions in it, but the predictions are comparable, I think. Yeah. No delay means that in your simulation, when you observe two galaxies merging, immediately you trigger the supermassive black hole merger.
So it should happen
Yeah, that will not happen. But if the time scales, because this happens in giga years, right? So if your time scale to drive your black holes to the center is 10, 50 mega years, that's pretty much instant.
So what is there any constraint on that? From anywhere, do we know that if two galaxies merge, black holes have to merge by n giga years? Is there a number like that?
I don't know that. I don't think there is any real constraint on that.
So someone was saying that there is an observation of 1.1 parsec separation AGN.
Yes, that was speaking about.
So is this in the gravitational domain completely, or still further? This point
It could be a bound line. It could be a bound line.
But what's
gravitational domain?
Yeah.
So
so
it might compute the delay, the like merger time from that.
yeah, you could if you have the masses, yeah.
This is from a merger history of this particular host galaxy.
No. The spiral is pretty undisturbed. I showed the image of the spiral galaxy. Pretty undisturbed, so it's probably like a minor merger. It's not that minor.
Right.
Where one of them is low mass.
One of them is low mass.
Not
Yeah.
a black hole, a galaxy.
Yeah.
The black hole masses are probably wrong.
What's the evidence? Sorry, I missed your presentation there. What's the evidence for that this is a black hole biology?
The double AGN, VLBI measurement of a double.
Two active black holes have been discovered at radio frequencies which show characteristics of an supermassive black hole. And they're located in the center of a galaxy. And the active black hole also shows the black hole doesn't run empty jets.
So there are jets
with
like
an S-shape or Z-shape. So there's evidence that the jet axis changed.
but is it accepted that it's really because of two black holes going around each other? Can it
Not
be
going
just
around. This is like a one-uniform measurement.
Yeah,
Two
it's
supermassive black holes.
And there.
Whether it's conclusive that
There's
it's
no
a binary.
proportion.
is it conclusive that this is like a binary black hole?
It's binary because we know the separation, we know how far this galaxy is. I showed the image of the galaxy. It's like a classic spiral galaxy nearby, extremely close by. And so, I mean, the galaxy was very well known to be one with an active supermassive black hole. This new discovery was the discovery of a second active black hole near the first one.
In ring.
In the at radio frequencies, yeah. Sorry. Is this still an idiom now? I don't know. But it was when it was
Yeah.
when the light left it to return. Yes, I'm sure they're planning but what they published so far is fine.
All right. So if you ignore delays, you're peaking at a redshift of around 5. But if you do implement delays in your heavy seed scenarios, because your black holes are more massive, they're harder to drive to the center. And this means that the time scales for the delays will be much longer, so they will have a large impact on the merger rate. That we can see here, it's quite dramatic. I think the assumptions made here were quite pessimistic, so I don't think it will be that bad. But still, it's something to keep in mind. Right. So what we did next with these catalogs of binary mergers is that we did a parameter estimation study in order to tell how well we can measure all the parameters of the binary with LISA observations. So for that, we used a Fisher matrix analysis, and we used spin precessing waveforms, circular and in spiral only. However, we compared that to a few data analysis results that used hybrid IMR waveforms in order to tell whether the merger itself helped you increase your precision on the parameter measurements. And what we found was that yes, it did increase your precision, but only on the extrinsic parameters, the sky location and the distance measurement. Like the individual masses, individual spins were not improved by the merger. So here the result from this study is that forget about the red lines. They're not that relevant for LISA. For LISA, the black curves are relevant, and they show how well you improve how much you reduce your error on the parameter in question versus how much excess SNR you have in the merger compared to the Inspiral only. So for the luminosity distance, you see this curve, which follows very well this curve, which is just 1 over the SNR ratio. And for the sky location, yeah. 2? This one? Yeah. This one, yeah.
You said something like for high mass binaries, inclusion of the merger Ringdown doesn't much affect the parameter estimation.
For some parameters, yes. Yes, because you can think of it this way. Here we're trying to measure the properties of the components. All right, we're trying to measure the component masses. So your waveform is affected by the component masses in the Inspiral because they're separated. But when they merge, there are no component masses anymore. All you have is the total mass. So that's all that you can measure. You cannot measure the individual masses anymore. Right? And same thing for the individual spins. Your individual spins affect your waveform only when they exist, right? Yes, 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 absolutely. But that's not what we're trying to measure here. So it will be present as a function of all the component parameters, but those specific combinations of these binary parameters will improve, like the total mass and the final spin, but that's not how we parameterize our waveform. So we parameterize it in terms of the components, Yeah. All right. And this curve here is for the improvement in the sky location, and it follows pretty much exactly 1 over the ratio square. Yeah.
If I know the parameters of the component
Yes.
Bodies in the binary.
Yes.
What can be said about the remnant? Like, is there a conclusive statement about what the mass and the spin of the remnant?
Of the remnant? Yes. Yes. You get this from numerical relativity simulations. So from numerical relativity simulations, you inject your components, you merge them, and you observe the remnant. So from that, you can recreate a function from, say, M1, M2 into M. Yeah, and there are people have been fitting these kinds of functions for a long time, and that's how we construct most IMR waveforms by using those functions. It's the ratio between the total SNR and the SNR in the Inspiral. Right? If you want, if I go back here, let's say this is your total SNR, and say your Inspiral stops 1 minute before merger, so this is your Inspiral SNR, right? Was the improvement in the measurement accuracy. Right. So if you have 10 times more SNR, including the merger, it means you can measure your luminosity distance 10 times better, and your sky location 100 times better. Yeah. Right. So we use those results to rescale what we found from our Fisher matrix study of the parameter estimation of the binary parameters. Right. So so first, how many detections did we get from all these mergers? So this plot is contains a lot of information. Not all of it is relevant. So when we made this study, we were comparing different configurations for LISA, say different arm length and different acceleration noise levels. So for LISA, you really only have to only this line here is relevant. So in the this is the absolute number of detections in LISA with the three different black hole evolution models. So in red, you have the light seeds model. In green, you have the heavy seeds with no delays. And in yellow, you have the heavy seeds with delays. So what we can see here is that so from this configuration to this one and this one, you reduce your noise level, basically. So here in the light seeds model, you get more detections as you decrease your noise level. But for the heavy seeds, you don't get more detections. And what that means is that you already detect everything in LISA in the heavy seed scenario. In the light seed scenario, you don't see everything. How well can you measure the masses? So for about a third of the systems that we observe, you can measure the component masses with accuracy better than 10 to the minus 2. Right. So, oh, I should have mentioned still. So in the most pessimistic scenario, we get about 40 mergers. That's during 5 years. And in the no delay heavy seeds or in the light seed scenario, we get several hundreds, say 400 to 500 mergers. Right. So can we measure the spins? Yes, yes we can. Unfavorable conditions though. But the spin of the primary, so the most massive black hole, we can measure quite a few times to better than 1% precision. And the spin of the secondary, because it has less impact on the waveform, we cannot measure it as well, but we can get 10% precision on the spin magnitudes. Right. Can we detect the spin alignment angle? That's yes, we can measure it to better than 10 degrees most of the time. And that's when that's where precession comes into play. That's you need to have a precessing waveform in order to measure that kind of parameter. But in our case, the spins were large enough, and the signals were loud enough that we were able to measure the alignment angles to within 10 degrees. All right. Now, one result relevant for cosmology is how many systems can we detect with better than 10 square degree sky locations, better than 10% distance measurement, and at redshift smaller than 5. In this case, we can point a future detector with a future electromagnetic detector with a wide opening angle, and we can with which we can detect a counterpart, which will give us the redshift. And since we have the distance, and it's not too far away, so that we can see the counterpart, then this will allow us to measure cosmological parameters like Arun talked about yesterday. So for this figure of merit, we find for the light seeds and the delayed model about 20 to 30 such measurements, and in the heavy seeds case we find 100. Can we confidently detect a merger in the early universe and tell that it's in the early universe? So here is how many systems we detected at redshift higher than 7 with better than 30% precision on the distance. And here we have a lot of measurements in the heavy seeds case, because we basically detect everything, and most of the mergers happen quite early. In the light seeds case, we get 40 to 50 because since the masses are smaller, we're not sensitive to such a high distance. And in the delayed case, we only observe a couple. And that's because of the delays. That's because those delays, if you have a galaxy merger at redshift 10, by the time your delay has expired, you're already at redshift 5, so you don't see a lot of things. Yes.
So you showed these localization, right? I think the previous slide.
Yeah.
So you know what the corresponding numbers would be in case of extreme mass transference?
No. So I don't know that quite yet, but so there was a similar study for EMRIs. I think Gare and Babak were the lead authors. Sorry. Yeah. 2017. Science with Lisa is the start of the title. Yeah.
So these are like single detector. So won't it be difficult to localize the source because it's on Earth?
Yes. That's exactly right. It's orbiting, so your detector plane changes during the year, so that modulates your signal in a way that depends on the location of your source.
But in the duration, like it goes to another location, the signal will pass through, and it will be no more there.
So for example, suppose that this is the orbit of Lisa, right? You have a source here that emits some gravitational waves. So when Lisa is here, your frequency is redshifted. And when Lisa is here, your frequency is blue shifted. But if it's in the other direction of the sky, it's the opposite, right? So that can tell you about sky localizations. And another thing is that when you're here, your detector is oriented like this, and when you're there, it's oriented like this. So you observe those patterns.
Frequency, the signal might change significantly itself. So
It depends on your source, yes, but still, you have a different effect from here or from here. Yeah. Better localization. Yeah. So this is this is not the best we can do, right? For loud sources, we can do much better. But what we wanted to do is that we looked at planned electromagnetic missions that would be contemporary with Lisa, and what's their field of view. And we took this number, which we took as 10 square degrees, to say, okay, if we detect a merger, can we take this detector and point it and see the counterpart? That varies a lot. You can get below 1 square degree. You can get 0.1 square degree, or you can get worse than 10 square degrees. That also happens. It depends on the source. Yes, yes. The distance, yeah, the same thing. You have systems for which you can measure it better than 1%. The closest ones, the loudest ones, you can detect it much better. But at Redshift 10, you don't get 10% accuracy. All right. All right. So, another sorry. So another interesting effect is the effect of the eccentricity. So so do we expect supermassive black hole binaries to be eccentric, or significantly eccentric? So there are a few mechanisms in order to increase your orbital eccentricity. For example, if you have triple interactions, these tend to increase your eccentricity. So depending on the mechanism that's responsible to drive, your binary close enough to merge, you can have high eccentricities, or you can have lower. And the measurement of the eccentricity will allow us to disentangle the importance of those different mechanisms. So in particular, one interesting case is that if you don't solve the last parsec problem and all your binaries stall when they're 1 parsec away, what will happen? So you have first a galaxy merger, and you form a binary that stalls at 1 parsec. But then a third galaxy comes in and merges with the galaxy that's already merged, and you have another supermassive black hole that comes into the system. So when this happens, you form a triple system, and with these triple systems, you have different mechanisms that can lead to very, very high eccentricities. If you have chaotic triple interactions, you can eject one of the black holes, and the two black holes that you're left with will be much closer together and very, very eccentric. So in this scenario, you create a very high eccentricity, and you harden your binary enough for it to merge. So that would depend on the mass ratios. Yes, absolutely. So one other thing that can happen if you have a triple system is that you can have a hierarchical triple. So you have a hard binary in the center with a wide binary around it. And in that case, what can happen is quasi-lead-off resonances, which is an interaction between the eccentricity of the binary and the inclination of the outer binary. And that can drive up your eccentricity as well. And if you drive it high enough, you can also lead to a merger like that. So this is a study that looked at those triple interactions. And here, they looked at the typical eccentricities that you expect from such interactions. So these are from chaotic triple interactions in blue, and in red from no, that's the opposite. In red, is for ejection. That's when you eject one of the components. And in blue, that's when you have those resonances. And you can see that even at ISCO, so you still get eccentricities up to 0.1 in that case. And during the Inspiral, the gravitational wave emission tends to reduce the eccentricity significantly. So if at ISCO they have an eccentricity of 0.1, that means that when they enter the LISA band, they will have extremely high eccentricities. And that's the next plot. So the red curve is more relevant for PTA. It's 10 to the 9 solar masses at 1,000 Schwarzschild radii. And the blue curve is the eccentricity that you expect when a 10 to the 5 solar mass binary enters the LISA band. So it's 100 Schwarzschild radii. And you see that you can get really, really high, up to 0.9 initial eccentricities when you enter the LISA band. So that will be a very, very important effect for modeling. All right. So what else can you do with LISA? You can measure the ringdowns, and you can measure the ringdowns really well. You have a lot of power in that range. So if you measure your ringdown modes very well, and you measure multiple ringdown modes simultaneously, what you can do is to test whether your remnant is a Kerr black hole or a different object. And that's because the frequencies at which the frequencies and the damping time for the last ring down depend on only two parameters: the mass and the spin of the black hole. So when you measure one frequency and one damping time, that completely fixes your mass and your spin. And if you measure multiple of them, you have independent measurements of the mass and the spin. So you can look at whether they're consistent or not. If they're consistent, then you're likely to have a Kerr black hole. If they're not, you have something else. So here's what you can do with LISA. So LISA is here, compared to different ground-based detectors. You have LIGO O1, O2, advanced LIGO, A+, etc., up to a Cosmic Explorer here. So the different curves, the different colors here for ground base are different mass distribution models. And the solid symbols tell you how many events per year you expect in which you can measure one ring down mode. And the hollow symbols tell you how many events per year you expect in which you can measure at least two ring down modes. So here you do see your ring down, so you can measure your remnant mass and your remnant spin. And here, when you're on this curve, then you can tell whether you have a Kerr black hole or something different. And in order to get one event per year, you need to get to be really far in the future, like Voyager or ET. In order to see that on the ground. In space, however, pretty much whenever you measure one ring down mode, then you can see multiple ones at the same time.
Which of this is the final LISA configuration?
This one.
N28.
Yeah, N2A2, yeah. So here we have our different population models. They use the same population models as in the other study. This is the light seeds scenario. And you have much fewer events here because those black holes have lower masses. So your ring down is no longer in the optimal range of the LISA frequency window. They're at a bit higher frequency than the optimal. But heavy seeds model, you can make really good Kerr-Nest tests. All right. So one other thing that you can do with LISA that's a bit surprising is that you can detect axions with the supermassive black hole measurements. And the way this works is that if you have very, very light Axion-like particles, very, very light bosons, you can in the near a Kerr black hole, inside the ergo region, if you create a pair of particles, and one of which carries negative energy and falls into the black hole, the other one is ejected to infinity and carries a lot of energy. And if it has the right mass compared to the mass of the black hole and the spin, it can bounce back and trigger what we call a super radiant instability. And what will happen then is that you will create a cloud of light bosons around your black hole, which will drive down the angular momentum of the black hole significantly. So you reduce your spin up to the point where you leave your super radiant instability. So if we make supermassive black hole measurements with LISA, we can measure the spins. So that means that if we measure lots of high spins, this super radiant instability obviously doesn't occur. So it means that we can reject the existence of bosons in this mass range just because we observe high spins. But if those axions exist, then they will create holes in the mass spin plane. And with your supermassive black hole spin measurements, you can see that. And here's a simulation. So this is the form of the hole that you create for if you have a 10 to the minus 16 eV boson. And between so a few 10 to the 4 and a few 10 to the 6, you drive down the spin of any black hole that's created inside this region. And here's the simulation of black hole measurements with LISA in this scenario, and you can clearly detect the presence of the boson, and in fact you can measure its mass up to 10% accuracy.
So this exclusion is from the current spin measurement from the AGNs, the exclusion part from the 10 to the 5 to the 6 part, the gap that you see?
This gap? No, that's due to the super radiant instability.
Yes, they cannot be. So the black hole should not. This spin should not.
Yeah, the black holes. Well, the black holes can have a spin like that, But if it has a spin like that, it will create a super radiant instability, and very quickly it will lose all its spin due to the super radiant instability, and it will reduce its spin until it reaches this this line.
That depends on the mass of the boson, right?
Yes.
So the fact that we have some measurements of spin of the supermassive black hole,
yes,
can be used to
yes, absolutely, yes, we can, yes, absolutely, we can, yes, it has, yeah. Yes.
If you have this kind of hole in the spin mass dot, it's like, can you confidently claim that it's a solution to the CP problem, CP problem, or if you have proved the existence of axioms, or there can be something else?
So it would, yeah, well, yes, it can be something else. So this kind of instability happened with very light bosons. It doesn't have to be an axion. It's just that if you have bosons in this mass range, you expect it to be an axion, because that's what your particle physics theory tells you. So this curve, right. So the spin, the maximal spin for when you are outside your superradiant instability depends on the mass of the black hole. It depends. And it depends on the mass of the boson. And the and this curve corresponds to one rotational mode. This curve corresponds to, so this curve is m equals 1, this curve is m equals 2, m equals 3, and m equals 4. Yeah.
So if it depends on the mass of the boson,
yeah.
which can be an axiom,
yeah.
so to draw the curve, you have assumed some mass.
Yes.
But then there's no like tight constraint on the mass, right? Right now we don't have any tight constraint on the mass of the boson, of the axiom.
Yeah. No, if we make this measurement, because the shape of the curve changes when you change the mass of the boson.
You've just drawn the shape of the curve. You have not. It's not a.
Yes. This is a simulation. Yeah. Yes. Yeah. Sure. A similar hole. That's a good question. I can't think of any personally. But yeah, I mean, sure. If you can come up with one, then that could be also a good explanation. Yes.
If the time scale of this Ringdown is sufficient so that it could
Yes.
actually even imprint on the gravitation.
Yeah. So the bosonic cloud that you create with this superradiant instability itself emits a gravitational wave signal, and in some circumstances you can detect this gravitational wave signal. Yes, but that's a bit different. Yeah. But the effect on the binary, I don't really think so, because when you create a remnant, that's when you start to spin down. But that's also when you stop measuring your signal. So I don't think this will really affect the. Yeah. It will move to the left or to the right. Yeah. Yeah, you can have multiple ones. Yeah. And then you will have the, what do you mean? The height of this? It's, yeah, it's more or less a fixed thing. It's for a given boson mass.
So do you have current, observational data which gives spin in this range for this mass?
So there are supermassive black hole spin measurements from X-rays, I believe, and you can use them to constrain your boson masses. Yes, but I don't think that you have any spin measurements at say 10 to the 4, 10 to the 5 solar masses. I don't think so. All right. So this is what happens when there is a boson present, and if there isn't, and we don't see anything, we can exclude a certain boson mass range with LISA. It depends a bit on the astrophysical model because so in this model you have lighter seeds, so you exclude heavier bosons. In this scenario, you have fewer measurements, so you cannot as confidently exclude your boson masses, etc. And as you get more and more time of observation, you can increase the range in which you exclude your boson mass. Yes?
Do you also assume some evidence for those bosons, like so they are comprising the total dark matter, like fraction of dark matter?
Oh, I don't assume anything. We just assume that so in order for these super radiant instabilities to occur, you just need this boson to exist. That's it.
Whatsoever, like rareness, like even if.
Yeah. Even if it doesn't really contribute to the to the matter density, because this is a quantum effect, right? That happens inside the ergo region of the black hole. So it doesn't depend on. It happens if you don't have any of those bosons anywhere. It's just sufficient to have this bosonic field in the universe so that you can create those particle pairs. Yeah, from yeah. All right. Okay, good. So I arrive at the end of the lecture. So I have to thank Chandra for suggesting I talk about the challenges in waveform modeling for each of the different kinds of systems that we can measure in LIGO, in LISA. So first of all, we can detect galactic binaries. What's the status of waveform modeling in that for those systems? So those are very simple systems. So we can model them pretty easily. However, there are certain effects that haven't been studied very carefully. For example, the eccentricity. So these can be eccentric, and if you have an eccentricity, you will have different harmonics present in your data. And if you can correlate those harmonics together, then you can identify an eccentric system and measure its eccentricity. But that has to be studied more carefully. Other effects can be important, like quasi-Lidov resonances, which could lead to time-varying eccentricities, for example, or mass transfer, which can reverse the sign of your frequency derivative, for example.
If the microplanes are eccentric, that would actually make the existing confusion noise projection to be, I mean, how much deviation will it make the existing?
That's a great question. I don't have an answer. Yeah.
This I can imagine will complicate math.
Yeah.
Side tracks.
Yes.
A lot of spread. And each
Yes.
one of them is going to have that. It's going to be a complete.
Yeah, yeah. I mean, it's not undoable. It's yeah. No, it's a great point. Yeah, yeah.
So from this eclipsing white dwarf binaries, there's no estimate of the eccentricity of the orbit. There are some eclipsing white dwarf binaries discovered.
Right. Yes.
UV.
Yeah, yeah. Well, I don't know if they have eccentricities for those, but yeah, yeah.
For them, maybe it is not. But this question is about the background itself.
Yeah, I just wondering if this could give some indication of the eccentricity distribution.
Yeah. Yeah, we have eccentricity measurements for the verification binaries already. Yeah. All right. For EMRIs, well, I won't spend much time on this. I'm not an expert at all, but the current status is that in order to have faithful enough waveforms, you need to compute self-force calculations at second order in the mass ratio. So you need to go to second order in the mass ratio. And that's still ongoing. It's been ongoing for a long time. I hear they're happy of the progress they're making. Yeah, we all wish them to be successful in that. There's also the fact that, as I mentioned earlier, the waveform has a very rich structure, so it will be very hard to detect. So we need good, efficient algorithms to just to evaluate the waveforms, but also to search for them. Then the big unknown, so intermediate mass ratio in spirals, those will probably be observable in LISA. The problem is that black hole binary waveforms, so post-Newtonian waveforms, they're very good up to say 1 to 1/50-ish mass ratio. Above that, there are other effects that influence the waveforms, which make pure post-Newtonian waveforms not the ideal thing to use. EMRI waveforms, on the other hand, they're very good, but already to have efficient models for 10 to the minus 4 mass ratio, you need this second order in the mass ratio waveforms, which is very, very hard to compute. So if you want to get to 10 to the minus 3 and go to third order, I don't think that's really a reasonable thing to expect. I might be wrong. So we need new ideas for for IMRIs because we don't have anything there. For stellar mass black hole binaries, for these ones, the eccentricity is also important because it can tell you about your binary formation channels, whether you are if you form your binaries in a dense environment, you expect high eccentricities. And if you form them in the field, you expect lower eccentricities. And this will be measurable with LISA. So this can give us good information if we can measure them. So here we're in the early Inspiral, so post-Newtonian is perfect. But they are at the higher end of the frequency band in LISA, so you really need to use this TDI response in your waveform modeling, and that's ongoing. And those waveforms will also have a rich structure comparable to EMRIs. So we also need good algorithms for and fast waveforms for detection. Right. Supermassive black hole binaries, finally. We expect very high signal-to-noise ratios, up to several thousand, so we need very, very accurate waveforms. We need multiple ring-down modes. We need spin precession. We need eccentricity. And we need all that together. And that's a real challenge. In this case, if you have low mass systems, then in the merger, you reach the higher end of the LISA band. So you reach the TDI regime, where you cannot just use the low frequency approximation. So you need to include that in your merger and ring down response. And yes, some scenarios predict very high eccentricities. Up to 0.9, and we don't have any waveforms to model such high eccentricities. We can reach 0.3, maybe 0.4, but nowhere near 0.9. So that's also that will also be very useful for LISA. And with that, I conclude the lecture.
Let's thank Antoine for this very useful and interesting session.
Thank you.